Hello everyone, and welcome to today's webinar. I'm a virtual avatar in Developers Shore. I hope you're all doing well and ready to learn. Before we get started, I just wanted to take a moment to invite you to become a member of the Great Devs. As a member of the Developers Shore community, you'll have access to our job opportunities, activities, and future webinars. You can join us by responding to our invitation email or completing the form on our website. Also, a recording of this webinar will be on our LinkedIn page. Without further ado, let's dive into today's topic. Please give a warm welcome to our speaker.
Hi guys. Today I'll be speaking about different ways of running, interpreting, compiling, and optimizing JavaScript. I really hope you will learn some interesting stuff about the code, JavaScript code that you already are creating, and maybe you'll learn how you can write applications in JavaScript that you didn't know you are actually able to. So we're going to have a journey from interpreter to just-in-time compiler to native code, and few additional ways of compilation will appear. We'll start with describing probably the most, I think not probably, the most popular JavaScript engine called V8, the most popular and also the biggest in the lines of code created for it. So V8 is JavaScript engine that is running your JavaScript in Chrome, in all the Chromium browsers, Brave, I think Opera also, Edge, as far as I remember, also is running on this, Node.js, of course. So really V8 is running most of our JavaScript. And well, it has to be some kind of a compiler or something, some kind of engine that takes your JavaScript code and runs it, transforms to some kind of machine code. But it's actually a really complicated. V8 started as a simple, I think, interpreter compiler. Right now, it has many layers, and it's interpreter, optimizer, and compiler, and all of those parts are running in different times, and sometimes at the same time, sometimes at different times. So we'll try to uncover what's actually in those layers and when they are running. First layer that is used to run your JavaScript code when we are using V8, it's called Ignition, and it is just a JavaScript interpreter, actually bytecode interpreter. So after your JavaScript goes to V8, it is turned into the bytecode, and Ignition is just going line after line and running the code. After Ignition, we have another layer, which is called Sparkplug. And this is first non-optimizing just-in-time compiler that is built into V8. So it takes the same bytecode that has been already used by Ignition, and it compiles into a bit. So yeah, it's non-optimized machine code, but it compiles to some static code that makes it run faster. And actually, yeah, so because it's non-optimizing, so it will use basically the same bytecode in the same version as our interpreter. The question might be, what's the use of it? If this is the same bytecode and there are no particular optimization. So it just takes Ignition execution paths. So sometimes some part of Ignition work, like going from one bytecode instruction to another bytecode instruction, can be just precompiled, and then it's faster for the CPU to run the whole program. And it makes so between the Ignition interpreter code and a Sparkplug compiled code, there is about 10 to 15% speed up. So even though there is no particular optimization, just precompiling the interpreter paths gives us a nice speed up. Then the third layer in V8 is maglev, and this is first just-in-time optimizing compiler. So just-in-time, I should mention, because this is another just-in-time compiler, just-in-time compilation means that there is no separate phase for running your code and compiling your code. So when your code is being run, for example, by the interpreter, compilers watch what is going on with your code, watch what arguments do you pass to your functions, watch types of your variables, and based on that knowledge they gather when code is being run, they compile just in time. That's why it's called just-in-time compilation, because it happens not before running, but at the same time as your code is being run. And maglev is first optimizing compiler, so it uses all this data, information about function types, information about variable types, and produces optimized, a bit optimized machine code. And this is first from two optimizing compilers. So it is quick to optimize, but it is also quick to de-optimize. So to show you a very simple example, in principle, maglev could see that you have created a function called add. And of course, in JavaScript, you can pass whatever type you want in here. So it can be an object, it can be even another function. So if maglev sees that you are passing numbers, then it will decide, okay, I actually know how to optimize for adding numbers. So I will emit machine code for this function that will be optimized for numbers adding. But if you just pass another type of argument, it will quickly de-optimize. So it gives you optimized version of your code, but it doesn't cost as much, and it knows how to quickly go to de-optimized version if it's needed. And there is the fourth layer called turbofan. This is third compiler, and this is also third just-in-time compiler in V8, but this is second optimizing compiler. So as I said, maglev is quick to optimize and quick to de-optimize. Turbofan allows you to produce even more optimized machine code, but it takes longer time and it gathers information longer before it actually optimizes, because the de-optimization from turbofan is not that cheap as with maglev. So it takes longer time, and also optimization and de-optimization is not that cheap in here. So it waits for longer, it gathers more information before it kicks in. So of course this is just a visualization. In reality, turbofan would need a bit more than 5 calls, but as a visualization, you can think that if it sees that you just run this function with the same arguments, but just few times, it still might not be sure if it should optimize already. But if you run this, another 100, another 1,000 times, it might decide, okay, now I gathered enough information to produce optimized machine code. And all of those compilers, as I said, are just in time, meaning they work at the same time when your code is being run. That's why it actually makes sense to have few of them, at least from point of view of V8 developers. Because first, our first compiler is just pre-compiling execution path of the interpreter, and it's not costly, so it kicks in fairly quickly. Then first optimizing compiler kicks in once it gathered some information about your code being run, and the third one kicks in only after it gathered really a lot of information about how your code is being run. So that's why it makes sense to have few of those compilers, and using these three compilers, V8 is trying to make your code run as fast as possible. So yeah, that's quite interesting that your code running in V8 might actually, through the whole lifetime of your program, your function, for example, might be sometimes run by the interpreter, sometimes by one compiler, sometimes by the other. And then it might be optimized differently. This is also one of the reasons why Chrome, Chromium, and all of the Chrome-based browsers take up so much resources. This is not the only reason probably, but one of the reasons, because all of this compilation, watching your types, just and optimizing and then de-optimizing, it just somebody has to pay for that. It cannot be done for free. So because you as a programmer of JavaScript, you do not check your types, you don't have, like, JavaScript doesn't have types. Somebody has to do it for you. Somebody has to trace what you are doing with your code, and somebody has to try to run it as fast as possible. So this whole machine just has to take up a bit of computer resources. Although, yeah, JavaScript, from your point of view as a programmer, is untyped, because even TypeScript is just a linter. It doesn't add types to the actual language. If you look, and you can break types in TypeScript. It is possible in many ways. So from point of view of programmer, JavaScript as a language is untyped. But from point of view of V8, it's actually, I would say, furiously typed. And I can illustrate that just showing you some types from V8. So as you can see, we are in Chromium V8 sources, and we have objects definitions in here. So these are objects definitions that V8 is using to represent your JavaScript code. So just short look can show us that we have around 20 string types, different string types, external, internalized, 1 byte internalized, string, slice string, fin string, so a lot of them. Then we have array also 12. I can already see about 12, 13 array types. We have different hash types, hash table, ordered hash map. To be fair, if you write JavaScript, I'm sure that you've never seen hash set type, like you've never written hash set constructor in JavaScript, but in V8, all of those types are used, and all of those compilers speculate which types will represent your data in the best way, so your program can be run performantly and not overuse memory. So this is quite interesting to see that you just see string, but V8 sees 20 different types of string in different times of your code execution. And those types are needed to perform optimizations, because to create optimized machine code, V8 needs to know what types are used in the program. Without choosing particular types, there is no optimization. But of course, you can go and check V8 sources, but you can also run your programs with proper flags, and you can by yourself see those types used by V8. And I will give you a few examples of that. I'll present you how can you do it. So node, every node. So you can, after the presentation, you can just spin up your node and just use this flag, allow native syntax. So every node can use this flag, and with this, we are getting access to some compiler instructions that are not available from normal code. And those compiler instructions are also used by, for example, V8 developers to see how their engine is, what their engine is producing, for example, what JavaScript comes out from their engine. And let me open terminal in here. Let's go to optimizations here and run a few of those. So this debug print instruction will show us the real V8 type of our variable, because we just see, okay, this is a number, but for V8, it's actually something else. And this will be, yeah, this is the first file. Okay. And here we see our type, V8 type, which is called SMI. I also, for clarity, I called this variable SMI, and SMI for V8 is something called small integer. So small integer is any integer that fits into 31 bytes. And this is a special type for V8 for many reasons. One of the reasons is that all the small integers are kept as V8 if it tries to keep all the small integers in processor registers directly. So they are not even heap allocated. They are not. There is no memory allocation for them. They are kept directly in your CPU registers if it's possible for V8, and it means that your numeric code, even in JavaScript, if you use just these small integers, might be optimized to really, really performant code. So in some situations, it is possible for V8 to take numeric code running on small integers and produce machine code that will be, fast, similarly to, for example, some C code. Because if the small integers are kept directly in CPU registers, then there is no memory overhead, no passing from from memory to CPU, and the operations might be really, really fast. Another number type that we can see how it's represented in V8, it's a bigger number, negative, and with floating point. So this is heap number type. So we can see already we have another type in here, and for V8, those two numbers are different types. We can have a look at string types. So string, this pretty short string is 1 byte internalized string. And if we, for example, make a concat, we use the source string and we concat with some other one, we're going to get another type. So this is cons 1 byte string type, which means that this is a type of strings connected. So this concat instruction, even though from your point of view, it just creates new string, in V8 memory, those two strings will be connected, and there is a specific type to represent that. And one of the reasons, of course, is just memory management. So instead of copying the whole string and allocating a new memory, this will be just kept as reference and a part of new string. There are, of course, array types. So simple array like that has a type of JS array and then packed double elements. So doubles are, of course, types of numbers in here, and this is packed, which means there are no holes. But if I add, for example, 2 empty elements in here, this changes to wholly double elements, and you can even see in the implementation of elements that the whole appeared on elements 1 and 2. And here we can also see that this is a fixed double array, which means that V8 decided, okay, I see that you have only 6 elements, so let me keep this array as fixed length array, because V8 in here does not assume that we will change the length of the array, so it is being kept as fixed. Similar thing also happens with wholly element when I, for example, add something at some index longer, somewhere past the indices that I already filled. So here it is wholly elements, and we have whole, but this becomes interesting because we have the whole on elements from 4 to 22, which is obvious because as we can see, there are no elements in there, but we also have a whole in here. And this means that after some number of elements in array, V8 is no longer creating a fixed array with the exact number of elements. So this is fixed double array, not with 24 elements, but with 52. So in here, V8 decided, okay, I see that you're adding some elements on indices later in the array. So let me allocate memory straight up for another, around 30 elements until 50. So this is interesting, which means that V8 has some prepared lengths for fixed arrays, and it decides, looking at your code, what amount of memory should be allocated for a particular array. And here we have allocation for 52 elements. And we can see what happens if I use index 223. And as you can see, yeah, still fixed allocation, but this time for 352 elements. So this is probably another fixed number, fixed length for V8, instead of just cutting array on the element 223. We have allocation for 352 elements. So this is some introduction into debug print. Besides debug print, we can also use something called get optimization status. And this will show us what is the optimization status of our function. So with this simple function that just takes an argument and adds a 3, here we have prepared bit operations. This is not that important what happens. It's important that implementation of V8 has this mapping that if this operation is true, then this is the meaning of our status. So we can just run it, get the status from get optimization status, and see what console log will return to us. So this is a function, it's true, and it's also marked for optimization, which is interesting because it has been called once, but well, it is marked for optimization. We can try to force the optimization or an optimization attempt. So this does not give us. We are not sure if the optimization will happen, but we can try to ask V8 for optimization on next function call. So let's try that. It actually, well, even though we asked for that, it hasn't been optimized yet. It's just marked for optimization. So apparently this V8, even if we ask it to optimize, it might not optimize every time. And we can also check status from within function and see what happens there. And if we check status from within, we see that this is a function marked for optimization, and the topmost frame is turbofan. So already in this little piece of code, it looks like turbofan optimization has happened, which is quite interesting. Okay, so these instructions allow us to check types of our variables and status of our functions. And also because, I told you that there are different optimizations that V8 can do for you, can perform on your code. Let's see how that works. So before we were using this allow native syntax flags. And here we are going to use trace optimizations and trace de-optimizations flag. We're going to start with simple add numbers function and run it, in a loop 1,000 times, so basically 2,000 times, because for each loop we call it twice. So this will be third example. And here nothing happens. So apparently running a function 2,000 times is not enough for V8 to go and optimize it. We might try to run it a bit more times. Oh, sorry, I have used incorrect flags. So let's start again. Trace optimization and trace de-optimization. Okay, but yeah, the case stays. So this is not enough for optimization. This loop, okay, this is enough for V8 to kick in. For turbofan to kick in and start optimizing. So let's focus on our add numbers function. We see that add numbers has been marked for optimization by turbofan, reason being small function, then compiling method was chosen, compilation completed, optimizing completed. So in here, V8 decided, okay, you really run this function quite a lot, so let me go on and optimize it properly. So instead of just interpreting, we're going to have properly optimized machine code for that function. And let's see what happens if we run after this optimization is ready. What happens if we run it with different arguments? So instead of just integers, we're going to use some floating points. Yeah. Okay. This is enough for V8 to de-optimize. So as you can see here, this is our add numbers function. There is a bailout, eager de-optimization, reason being those numbers are not small integers, not a SMI, which is true. They are not integers. Even though they are small, they are not integers anymore. So different optimization happens in code, in V8 code. For small integers, different optimization might happen for numbers. And let's see what happens if after this de-optimization, I run add numbers again quite a few times, but this time with floating points. So we have first optimization completed. Optimizing, yes, so there is marked for optimization. Optimization is completed. Then there is our bailout, as before. So function add numbers, reason being not SMI, is being de-optimized. But after that, add numbers is being optimized again. So here, marked for optimization, reason being small function, compiled, optimized again. So in this piece of code, there will be optimization of add numbers first for small integers and second for different numbers. And we can even see what happens once we run small integers again. And we have then two bailouts, yeah? So we have first compiling here. Here we have marking for optimization, compiling, marking for optimization of add numbers. We have de-optimization of add numbers. Then we have another optimization done, and another insufficient type feedback, another bailout from optimization, insufficient type feedback for compare operation, and that's it. Add numbers is not optimized. Here we have some optimization, but this is some unnamed function, some anonymous function. So add numbers has been optimized twice and de-optimized twice. And in this loop, it's no longer optimized. So here we are running de-optimized code. So you can see V8 does not like if you change types too often, argument types too often. And those types, even from your point of view, this is a number, this is a number. And in JavaScript documentation, you won't find this difference. But for V8, those are different numbers. Another funny example that I wanted to show you, because mainly this is for, I would say, for interviewers. If you go for an interview as JavaScript developer, and you have interviewers who like to ask tricky questions, sometimes people might, for example, ask you about optimization of error handling. And some time ago, V8 was not able to optimize error handling. And I think as I was preparing the presentation, I found some information like that still on the internet. But right now, we can see that if we create add numbers function with try catch in it, and we run optimization, de-optimization, add with try, add numbers is being marked for optimization, and there is no de-optimization happening. So this is optimized by V8 with no problem. Two more examples that I'm going to show you. Let's start with number, this is just number, and this is value. Yep. So here we are going to have a function add value, which just takes an object and adds a value to it. So really quite simple, and then returns the object. And we are going to run the function on 100,000 of objects. So this is example number 5. Let's see. We have add value marked for optimization, and yeah, compiled, optimized, everything nice and dandy. Then what happens if we, after that, we run, for example, just number. So object with the same keys, but different values. So here just number is 1, and here just number is array of strings, actually, and here number is also a string. So let's see what happens with our optimization after that. Actually, nothing bad. So add value is being optimized once, and no de-optimization happens. But if I go one step further and say, yeah, actually array, so I change the key of my object. Okay, here we are getting information. Okay, I need to bail out from this optimization because there is a wrong map. You have given me a wrong map, so I'm de-optimizing. I no longer use the optimized code for your add value function. Although after this bailout, the next optimization happens, so we're going to have optimization, de-optimization, and next optimization for the new shape of an object. And let's see what happens if instead, because here we modify an object and return the source object, let's see what happens if we take source object and return a new one created out of it. So optimization happens, compiling, yeah, compiling, optimizing, everything done. And let's see if I pass, instead of an object, I'm going to pass an array, so totally different shape, totally different type. And here, even though we have the optimization, this is, and it looks reasonable, insufficient type feedback for call, this de-optimization does not happen for our add next field function. So it happens for some anonymous function, although I would have to dig into bytecode directly and check what function is that, and maybe not this time. But this is quite interesting, that our add next field, even though we used different type in here, is not getting de-optimized. So I really invite you, after the presentation, to just open your node. Like I'm using node version 20, not the newest, but not that old, and just use those flags and have fun with your JS code and see what gets optimized and what gets de-optimized. Okay, let me, find everything. So this was a bit of console time. I have shown you how to actually check V8 under the hood and see what types are being used for your variables, and also how V8 optimizes and de-optimizes your code when it happens. And this is all nice, but as I said, the cost of that is huge. V8 is a huge JS engine that takes up really a lot of our resources. So one of the first questions that might appear when you look at it is, okay, but this just-in-time compilation is really nice, but maybe we actually can save up some resources and compile JavaScript before. So just do ahead of time compilation like we would do with C, Go, Rust, and other compiled languages. Maybe we can try that with JavaScript also and save a bit of our computer resources when we just want to run a simple script. So creators of Hermes engine that's being used in React Native decided that they will give it a try. And they created an ahead-of-time optimizing compiler designed for mobile devices. It is actually not that weird that they designed it for mobile devices, because mobile devices has less, they have less resources. But also, for example, iOS does not allow any external just-in-time compilers to be run on it. So the full V8 won't be allowed to run on your iOS device for security reasons, because just-in-time compilation might introduce, I'm not an expert in that, so surely in the security cases, but because we are compiling and decompiling our code live, it might introduce security issues. So Apple just does not allow it. So first reason to create Hermes is to save up on resources and compile before running. And second reason is that just-in-time compiler from external providers is forbidden on some mobile devices. And Hermes is already available. You can just right now use it if you write React Native. But the issue with Hermes is, okay, so it compiles before, it compiles ahead of time, produces some bytecode to be run, but it doesn't have all the information that just-in-time compiler has about the types, about the ways that you run your functions, types that variables you pass to your functions. So in principle, it has to be slower than JIT because those information are just not there. And one of the branch that Hermes is developing right now is called static Hermes, and they decided, okay, let's try to make JavaScript properly type, so we can actually have all the information before the compilation and produce some nicely optimized machine code. So Hermes is just doing ahead of time compilation into the bytecode, which gives us some optimization, but not all the optimization we could actually do. And static Hermes is, so as I said, and static Hermes goes a step further and takes language that looks like TypeScript and makes the types in TypeScript sound. So sometimes if you write TypeScript, it does, linting for you, but you can still break it. And with static Hermes, you're going to have more errors before you run your code, but then you will get a properly optimized code with sound types. And then we really are entering a new era of JavaScript compilation, where we get ahead of time compilation into nicely optimized binaries. So we really can, in the future, we should be able to, have our JavaScript code should have performance really that might be in realms of some of your C code. Maybe it depends on how good the Hermes compiler will work. Can we use it today? So static Hermes is not, by default, it is not enabled in React Native for sure. It is still in development, but there is static Hermes branch on Hermes repository, and there is a whole discussion on GitHub how to use static Hermes, so you can go and check. Although I have to admit, sometimes I'm having issues with building new version of static Hermes, but maybe you're going to be in luck. For example, about a month ago, I had no issues. Right now, I have some issues trying to build the latest version. But maybe you can just, for example, go and check out the version from a month ago. So this is really, really nice, and I really would like to see development of that, because then we'd have the sweet spot for JavaScript when you can start writing your JavaScript without types, but then when you need optimization, you add your proper types, and static Hermes will produce a really nice optimized machine code for you. So this was Hermes. We went through V8, we went through Hermes, so just-in-time compilation, then ahead-of-time compilation, and then we are entering step 3. Do I really need optimizations? And the question, the answer to this question is it depends. So if your whole application and your huge application is written purely in JavaScript, then probably, yeah, you need optimizations. But if you treat JavaScript as a scripting language for some bigger system, then you might not need those optimizations, actually. And in such cases, you can use, for example, one of very small, interesting engines that popped up lastly and that are getting some traction in last years. So, for example, Quick.js. Quick.js is a fairly new JavaScript engine built by Fabrice Bellard, who is also an initial creator of FFmpeg, so set of codecs for audio and video that are used in almost all our audio and video programs. And he created this small JavaScript interpreter written in C that compares to a really small binary that's around 1 megabyte, between 1 and 2 megabytes. The issue with Quick.js is that it's just a language, just interpreter of a language, without any libraries, without huge standard library, without tooling. So what can you use it for? Well, it is quite interesting because it's written in C, and you can add C bindings to C libraries that are already created, and it's fairly easy. One of the most interesting ones are bindings for Raylib. Raylib, if you don't know, is this really fun game library working in immediate mode. And I'm going to show you a little example of what does it mean and how it works. So first, let me open the code and let me show you just a very simple example of a game I created with Quick.js and Raylib. So just a little labyrinth game where you have a player that moves around and has, light that is being blocked by the walls. So this is basically the whole game for now that I just created. And this is the code for the game. And immediate mode means that instead of having separate game state and separate drawing code and some kind of I don't know, event loop or reactive connection between state and what's written, what's drawn on your screen, you have just one function, basically one loop that is being run. The body of this loop is being run on every frame of your game. So for every frame, we check, okay, is enter being pressed at this current frame? Is key up? So if I'm pressing up on my keyboard, if I'm pressing down on my keyboard, then perform this action. And for every frame, I'm doing a wall collision, for example, so this light being blocked by walls. I'm also doing this on every frame. And it means that you need to actually change the way you think about writing games, but the code is way easier. So just for fun and for some small games, I really think this is beautiful library. And the fact that we can just write in JavaScript games that will run on your computer natively, because the engine is created in C. So as I said before, Quick.js, when you have whole of your program written in C, so the whole game engine is written in C, and you are just writing some your logic and you describe what should be drawn in JavaScript, it doesn't matter that this is JavaScript and this is Quick.js, which is unoptimized JS engine. It will still be quite performant and you don't have to worry. So this is one of the most fun ways to use Quick.js, and I quite encourage you to go on and check whether you'd like to build some fun games in JavaScript with really performant game engine running that. And Quick.js is getting more and more traction lastly because it was used by React Native competitor called Lynx to create their own JS language. So based on Quick.js, Lynx created Prim.js. They modified it a bit so it's faster, more performant. And using Prim.js, they are able to use JavaScript in similar manner. So as a scripting language for the huge engine, this time not game engine, but engine to create mobile apps, that is written in performant way, and then you are writing your logic, your scripting part in JS, and then it really doesn't matter that prim.js is probably slower than V8, because V8 itself, if you'd like to put V8 there, you'd have to pay, I don't know, 50 megabytes of space, like 60 megabytes, because that's, I think, the tiniest Electron app you can build is around 50 megabytes. And QuickJS or prim.js, instead of using 50 megabytes, you can use around 1 or 2 megabytes of space. So this is really a huge win, especially for mobile apps. And this is just enough for such cases where JavaScript, where your whole application is not written in JavaScript, but is written in something performant, and you just want to write your logic part in JavaScript. Okay, so quickly to sum up what happened in our presentation. JS as itself, JavaScript is just a language, and it has some specification, but it has many different implementations, and I have shown you 3 of those. First one was V8. It is a huge interpreter, just-in-time compiler, optimizer that allows for really good performance, sometimes on par with C code, but it might take, and usually it does take, a lot of your resources. Second one was Hermes, which is ahead-of-time optimizing compiler built for React Native. And of course, because it's ahead-of-time compilation, it uses less resources. And in the normal version, it will probably be slower than V8, but it implements its own type-safe JavaScript version to allow for really nicely optimized compilation. And I really hope that this is a future of Hermes, and static Hermes will win, because the connection of being able to write JavaScript and add types when you need them and then get properly optimized code is awesome. It's probably the best we can do with JavaScript. And the third engine I shown you is QuickJS, which is small JavaScript interpreter that can be compiled into small binary, allows easy interop with C libraries, like Raylib, for example, and for cases where you, for example, want to run some small script that will not be living for long, or when you need a scripting language for bigger system, QuickJS is really awesome choice. And I know that Amazon is using QuickJS for some containers that are short-lived, and for containers, for example, because if your code is short-lived, then it really doesn't make any sense to spawn up a huge V8 with the all JIT magic. If the script you run will live for 5 seconds, then QuickJS is really better option, because the optimizations in V8 needs a bit more time to actually kick in and pay off. Okay, and just a little postscriptum before I'm done. If you don't want to, if you're even a web developer and want to create web apps, you don't need to write JS. You can use WebAssembly and, for example, write your web apps in Rust. I also tried that. So the performance of WebAssembly is not that great yet. It will be slower than, for example, properly optimized JS by V8. But honestly, this is just fun. And there are a lot of libraries in Rust to create web apps. It looks, if you squint, it looks almost like React. And as an example, I created this small application, gradient drawer, where hello developers, sure, when I just can have fun with some gradients. And it is not a huge application, but this is fully written in Rust in it's around 180 lines of code, and it's just really fun. And if you want to leave all the JavaScript craziness and just-in-time compilers and other different compilers, you can use language like Rust. Although performance is not there yet, but in future we might have better performance. in future also, we're going to have WebAssembly garbage collector. It is already implemented in Google Chrome, for example, for languages like Java. So what algorithm in Google spreadsheets for drawing, as far as I remember, for drawing cells and drawing sheets on the screen is written in Java and compiled with WebAssembly garbage collector. And if the WebAssembly garbage collector is available in your browser, so if you run new Chrome, then the Java algorithm will be used. If it's not available, then it will fall back to JavaScript version. So it might really be the future for some applications that using WebAssembly in the future might really pay off. Yep. So you can just go on and build a lot of interesting applications in JavaScript. As I have shown you, there are different engines for different cases, and you can even write small script for your everyday use with Quick.js if you need, and you don't need to spawn whole huge JS engine. You can already compile JS to binary and write fast small apps. You can try this with Quick.js, and you can already try that with Hermes. You can write web apps in Rust and avoid just-in-time compilation, just compile to WebAssembly. And I think for really most of cases, you might even find performance to be enough. And you can, and I actually invite you to do it, you can just write JavaScript and learn about those engines, learn how the optimizations work. I've shown you few instructions you can use in V8 to see the types, to see how your code is being optimized and de-optimized. And then you can learn how to make sure that your code is, even though it's still good old JavaScript, it might be really, really fast. So yeah, go on, write JavaScript, write all the applications, and learn how to optimize them properly. Thank you so much. That's contact to me. I'm not that often on Twitch lastly, but I hope I will get back to Twitch and have some fun with JS and CSS and web apps in there. Thank you so much. Do we have any questions? I see a question. Do you have any tips on finding code that is using high CPU? Finding code that is using high CPU. Well, so it depends, but surely you can check for. Okay, so let me think for a second and answer properly. So, of course, you can go on, like the easiest way in Chrome to check if code is using high CPU will be using a DevTools. So probably, yeah, here, for example, taking a performance snapshot. So if you run your web application, okay, it's a big node project. As far as I remember, you can also connect Node to Chrome DevTools and then just take performance screenshot. And this probably is the best way to find what's using CPU. This should be enough, connecting with Node to Chrome DevTools. And using those flags that I've shown you, well, you can check. Of course, you can go and run your Node code with trace optimization and trace de-optimization. So it will not show you how much CPU you are using, but it will give you some hints. So if you see a lot of optimizations and de-optimizations happening, then you know that it will use more CPU. If you don't see optimizations at all, then also it means it's bad, because it means that your code is being run in non-optimized version. And if you see that you run your code and you see a lot of optimizations and no de-optimizations, then probably that's the best situation. So yeah, I would say two ways to find code that's using high CPU. So connect with DevTools and just take a performance screenshot and trace optimizations and de-optimizations. And if you see a lot of de-optimizations or you don't see optimizations, then you can be sure that more CPU will be used than it has to be. Okay. I think that's it with questions. I don't see any more. So if you have some more questions, just write me an email or find me somewhere internet. I'm happy to have a chat about these topics and many more about JavaScript, Python, or Clojure. So thank you so much. Hope you learned something interesting today, and have a good rest of the day. Thank you.
Our webinar has come to an end. I'd like to extend a big thank you to everyone for participating, and a special thank you to the speaker for a captivating topic. It was a pleasure having you all here today. Have a great rest of your day.